what we're going to find is as we dive into chapter 7, we're going to shift gears considerably from what we've been doing in the past couple chapters, which was looking at reactions and energy in a very, or we did a lot of calculations basically. Now we're going to kind of shift gears and go from talking about things that have sort of, tangible, let's look at it this way, tangible matter and how matter interacts and reacts with the world. We've looked at that quite a bit lately. We're now going to take a step sort of in a different direction, where we're going to go back to looking at atomic structure. Now, the reason we're looking at atomic structure again is because the model that we left off with, which was that Rutherford model, right? The model that had a nucleus surrounded by an electron cloud, is a little bit too simple for all of the things that we need to be able to do from here on to the end of the term. And what I mean by that is, what we looked at there was just this simple model where we had protons and neutrons in the nucleus, and we didn't describe how the electrons surrounded that nucleus. And we need to know how those electrons surround the nucleus, because those electrons are important in things like bonding. And so the next step in our moving through chemistry is now, okay, let's be more specific about describing these electrons, because these electrons are the things on the outside of the atom. They're the things that interact with other electrons of other atoms to form things like bonds and the like. So we have to take and get a better look at how electrons exist around that nucleus, okay? Now, to start down that path, we actually have to dive into light, okay? And so light is an important thing for us to look at because of how light interacts with matter. And so the first section of chapter 7, electromagnetic radiation, is just a fancy name for among other things, light. And when I say among other things, there are different types of waves associated with electromagnetic radiation. We'll talk a little bit about that. But what it is, on the whole, is just a way that energy can move through space. Okay, and so that's an important thing for us. Energy can move through space. Now, when we think about electromagnetic radiation, we can sort of, in our experience, understand it as being, hey, the light. When I turn a light on, that the light moves from one place to another, illuminating a room. Now, energy is moving through space as that happens. The other ways that energy can move through space are things like when you lift something, you do work on something, right? You're moving an object, and so that object moves from one location to another because of the work that you put in. So there's energy. You could think about it as heat energy moving from one place to another based on this temperature difference. If I have a piece of metal wire that I heat up, that energy, the heat travels through the wire because the wire conducts both electrical but also heat energy. And so these are some different ways that energy can move through space, but light is really important because light is the way that we see the world. And so electromagnetic radiation that we're going to look at is going to be related to light, whether that's visible light, ultraviolet light, infrared light, and then there's some other types of electromagnetic radiation that we don't really consider to be light in the same way, but it's related to light because it is still how energy transitions and moves through space. Now, in the history of electromagnetic radiation, the understanding of it and this long studies of light and how light interacts with things, is really understood to move with wave-like properties. Okay, so wave-like properties are a big key to early understanding of electromagnetic radiation. And when you think about a wave, right, a wave travels through space, right? It has wave peaks and wave troughs, right, where the peak is up at the top here, right, a trough is down there. And as that wave is moving through space, right, it travels, hits the peaks and troughs. And there are some characteristics that we need to identify to help describe a wave. And that's the first thing that we're going to do, talk about how do we describe a wave. And there are three things, three characteristics. Okay, those three characteristics are the wavelength, okay, the frequency, and the speed. Okay, now the wavelength is just, as you can see here, the distance between wave peaks or between wave troughs. It should be the same distance, right? This, you can see that those distances should be the same, or they are the same. And that's going to be measured in terms of meters, right? So you can say, okay, or maybe nanometers, but it's a length, right? It's a wavelength. Another one is frequency, right? So if I think about this wave as traveling through space, right? So this wave is moving through space and it's going in this direction, okay? The frequency is how many of those wave peaks would pass a given point in a certain amount of time, right? So how many wave peaks would pass this point over the course of some type of time, right? And so the number, the frequency is the number of peaks, right, or cycles, as it's often described, that pass a given point per. That should be second. Spell check didn't work for me there. Per second. Okay, so that's measured in hertz, where 1 hertz is just 1 cycle or 1 wave peak per second, and we think of the unit of frequency as being 1 over seconds, because we don't necessarily need to say 1 cycle per second or 1 peak per second. It's just every second, you know, per second is how many peaks pass per second, how many of these things happen per second. That's our frequency. Now, when we look at speed, right, the speed of electromagnetic radiation, we abbreviate that with C, and that's the speed of light. Okay, so speed of light is really measured as speed of light in a vacuum, okay? And so we consider the speed of light, right over here, you can see in a vacuum or in air, because light does travel through different substances at different speeds. However, in chemistry, we really only tend to deal with light how it moves through air, which is similar enough to a vacuum as to not really have a tremendous effect on its speed, okay? And so when we look at light, the speed is going to equal the wavelength times the frequency. So if we look at units there, right, so we can think about units of wavelength are meters. Okay, so there's our wavelength. And the units of frequency are 1 over seconds. And so if we multiply the wavelength and the frequency, we get a speed, right? So meters per second, okay? Yeah. Something else that's kind of useful for us and will be going forward is this equation can be rearranged really easily. That can be a useful thing. So if C is equal to lambda lambda times nu, something that's useful for us, we're going to find that the frequency of light is related to energy later on. And so it's useful to be able to calculate frequency or wavelength of the light. So nu is going to equal C over lambda. So you can rearrange that equation in multiple different ways. Okay. Now, something. So those are the basic things for us to understand. Is just the frequency, the wavelength, and the speed. Now, we're not going to worry about some other aspects of how light travels through space. It's actually traveling through space as a combination of 2 different fields, an electric field and a magnetic field, that are perpendicular to each other as it moves through space. And that's something that, if you want to explore that a little bit more, a physics course on light and optics would be a better place to tackle that, how it works, because you'd actually be able to do some experiments with light to show you how that's important. For us, what we need to know is speed, wavelength, and frequency of light, and how those 3 things describe how that wave moves through space. Okay. Okay. So when we look at the different frequencies of light and wavelengths of light and how they relate to things like the colors that we use and we see. Well, if we really just think about the visible light that we deal with, the visible light that we deal with on a regular basis is only a very small part of what we call the electromagnetic spectrum. Okay? So the electromagnetic spectrum is a spectrum that shows how wavelength and frequency are related to each other for light. Now, if we just look at the visible spectrum, right, and we expand that out, these are the colors we see, say, through a rainbow, or if you will, what we all learned in elementary school, right? Red, orange, yellow, green, blue, indigo, and violet, right? Roy G. Biv. And we'll find that that order is, the Roy G. Biv order is wavelength from the largest to the smallest wavelength. Or if you think about frequency, the frequency from the smallest to the largest frequency, right? Because as we can see from our equation up here, right, the frequency is inversely related to the wavelength. So as the frequency goes up, the wavelength goes down. And so in our visible spectrum, it's only a very tiny portion of that spectrum, but outside that we have some other parts. Okay, so if we go from, I suppose my visible spectrum down here is the opposite direction of the one that would be up here. If we think about the wavelength, right, so 10 to the 4th, 10 to the 6th, 10 to the 8th, so we have an increasing wavelength on this one from left to right. And so as the wavelength increases, you go from the visible region, where on the longest wavelength in the visible region, right, that's red, you can see here, right, around 700 nanometers. And so just outside of the red is the infrared, right? Whereas if we're on the other side of the visible spectrum, right, the shortest wavelength is on the order of 400 nanometers, and that's our violet light. And so just outside of violet light is the ultraviolet region. Okay. We're going to find that these different categories, if you will, of radiation, they're given these names based on certain things about their discoveries, right, about where they lie, right, ultraviolet, infrared, they're just outside the violet or the red region. And they actually have, there's a relationship with these different types of radiation, electromagnetic radiation, to the energy that they have, okay? So some other ones that you might be familiar with are microwave radiation, so the radiation that you use to, say, heat up your food. And the reason that's really important is that is radiation that's on the same energy level as vibrations of atoms. So that's why your food heats up when you hit it with radio or with microwaves, is that it causes vibrations in the food, which ultimately increase the energy of the food through those vibrations, and the temperature goes up. Right? We also have radio frequency, so that's radio waves that nobody actually ever listens to radios anymore, right? We all have a satellite radio and all that, but old school AM, FM radio frequencies, right? Those would be another type of electromagnetic radiation, again, energy traveling through space, okay? So if you're interested, one of the things I'm going to do here is check out this wave simulation. If you want to think about how a wave moves through space, this simulation, the simulation for a wave on a string, let me see if I can make sure I'm sharing the right screen with you. So if you click on that link, you should get this image here, right, this web page. And that web page is a good place to start to think about waves and visualize waves. And you can just click on it. When we tend to think about light, we think about light energy that's being given off consistently. And so the way I'm going to set this up pause this for a second. We're going to do this in slow motion. We'll restart it here. And I want you to sort of see how a couple things occur, right? How a wave travels through space and sort of what happens to the medium through which the wave actually travels. Remember, the wave is a way that the energy transfers through space, not necessarily the way that the matter is moving through space, okay? So if we take and start this wave just with this little wave generator here, a little oscillating piece of metal that's attached to a string, you can see how the wave will propagate through the string, okay? So I'm going to start it. It's in slow motion. You can see the wave's energy is moving along as the string sort of goes up and down with the wave, right? But it moves along in the direction of the string, okay? And you can see these wave peaks travel. If we want to, I'm going to pause that and restart it. Let's pick this first green ball here, right? And we can see that the frequency is related to, well, how many wave peaks pass that? So one wave peak now, a second one, and a third one, and a fourth one, etc. Right? So these are wave peaks that pass that given point in a certain with a certain frequency, right? So the frequency is how many wave peaks per second pass, right? So that's why it's in 1/seconds. The wavelength is just the distance from one peak to the next, and the speed would be the speed with which it travels through the string. But one of the key things here is, even as the wave is traveling, you notice that this green ball here is not traveling with that wave. So if we restart it again, the wave is moving, but these little balls stay in the same spot on that string. So the wave is moving through space, while in this case, the matter is not. So the wave is propagating or moving through the matter. So the energy is moving through the matter in this case, okay? Okay, so that's sort of a quick overview of how waves move. And so it's kind of a fun one to be able to see and visualize the movement of a wave. So we'll go back over here to our PowerPoint. And we'll just utilize our equation from the previous page to sort of think about the relationship between frequency and wavelength, just using that original equation that we had before, where C is equal to lambda nu, okay? And so here, in our example, what is the frequency of electromagnetic radiation associated with light having a wavelength of 513 nanometers? Now, before we do that, I want to come over here and point out, light with 513 nanometers is right in this region, right? And so that light would be green light, right? So if you actually look at the wavelength of light and the color of light, those things are related to each other. So you could figure out, if you know the wavelength, you could look at a spectrum like this and you could determine the color of that light, right? So just to do this, we really want to, if we want to figure out the frequency of light, so nu is going to equal C over lambda. And our value for C, if we go back here, I'm going to point this out, is the speed of light in a vacuum is constant, at least in a vacuum it is, right? That, again, that has a different speed in different media, but for us, we're dealing with it in a vacuum pretty much all the time. And so our value here for the C is 2.9979 times 10 to the 8th meters per second. Okay, 1 second, guys. Okay. And so that will be divided by 513. This is in nanometers, right? So we need to make sure that we're actually writing down what nanometers means, right? Since our units in the numerator, notice the units in the numerator are in meters, we need to make sure that our answer is going to be, or rather our denominator is also measured in meters, not the nanometers necessarily that we're given here. And so that's one of those things to be careful about, is changing that from nanometers to meters, okay? So 513 nanometers, all you have to do is put in the definition of nano, right, which is times 10 to the minus 9 meters, okay? And you just basically plug that into your calculator. So this is a pretty easy calculation, but you got to be careful. Now notice it's 513 times 10 to the minus 9. It's the same, which is the same as 5.13 times 10 to the minus 7. So be careful about that in your numbers. 513 nanometers is 513 times 10 to the minus 9 meters. And you plug those in, the meters cancel out. You wind up with a value of 5.84 times 10 to the 14th, 1 over seconds as our units, which is the same as 5.84 times 10 to the 14th hertz. Okay. And so that's just a quick, easy calculation of nu, assuming you have the wavelength. Okay. So what's nu? C over lambda. All right. So that kind of leads us into, now that we have the relationship between wavelength, the frequency of the wave and the speed, we needed that sort of as a foundation for talking about some things that were known about matter and energy, really historically speaking, and as far as what scientists knew about both matter and energy, because these are going to be important aspects for proceeding through a new understanding of atomic structure. So basically at the end of the 19th century, people understood that there was light or electromagnetic radiation and there was matter. Okay, and they were understood to be very different, to have very distinct properties. Now, when we think about matter, matter is objects, right? It's that a baseball or a piece of something, right? Something that has matter that we think about. Okay, and that's tangible to us. Whereas energy or electromagnetic radiation, light, is not quite so tangible, right? We turn on light, it illuminates something, but it's really hard to describe light from a standpoint of, well, what is it? How do I interact with it? Because I don't touch it, I don't feel it. Yeah, I can see the light, or can I, right? The light that we see is illuminating things in certain ways that allow our eyes to pick them up. And so the understanding of matter versus light was very different. Matter was understood to be particle-like. When we say particle-like, right, it has mass, has a size to it. It moves through space like a little tiny ball or an object. And the mass is something that we can know. We can measure the mass, and we can measure the position. And for that matter, we can measure speed of a particle as well. Right? These things, these descriptions of matter allow us to understand what a piece of matter is, how big it is, how fast it's moving, those kinds of things. And it's tangible to us. It's something we can literally feel with our hands, right? Whereas when it comes to energy, energy was understood to be wave-like. Okay, so when we think about a wave, and you can think about the ripples in a pond like we have here, right? If you throw a pebble into a pond, right? You throw a pebble in there, those waves are going to propagate out in all directions, right? And so as that wave propagates out, what's going on is the energy that's associated with that pebble we threw into the pond, right? That energy is being dispersed. It's moving away from where it was through the medium of the water. Now, if you were to throw a second pebble, right, somewhere up here, for example, right, that energy would also disperse out. And so you get these peaks, right? You can see these are peaks here, right? Unfortunately, my drawing is bad. Let me try to make that a little bit better. Okay, so you've got wave peaks along here, peaks, right? It propagates out from that central point. In between those wave peaks, you have troughs. Well, from this wave here, you've got peaks also, right? Peaks. Okay, and you can see that where you start to get wave peaks that intersect, right? If you have, for example, in certain regions, you'll have wave peaks from these two waves that start to intersect. And that's where you start to get interference, okay? And the interference that you can get is either constructive or destructive interference, okay? So constructive interference is when those wave peaks are in phase, right? So those peaks are in phase with each other. When we say in phase, right, we're looking at where the peaks of two different waves that come in contact with each other, right? So they're in phase. If, however, those peaks are out of phase, right? The peak of one wave encounters the trough of another wave, right? Or the trough of the first wave encounters the peak of the other. In that case, that's destructive interference, right? They're out of phase. If we have two waves that are in phase with each other and they have constructive interference, the resulting wave is actually twice the amplitude. In this case, if it's the same amplitude, when we say amplitude, we're talking about the height of the wave, right? So they add up, right? You get a much higher amplitude when you get the constructive interference. If you get destructive interference, they cancel out, okay? And so you would wind up with no wave at the point where these two were to add together. Now, when it comes to light, light was known to act in a wave-like manner. And so if you were to take light and say from a light source, the light left the light source here and started to propagate out. And so it acts as waves. And again, there's some really neat experiments that you could be able to do in a physics sort of a light and optics type course. But basically, if you take this light source, what people knew is that you would get light that if you shine it through a slit over here, you would get light coming out here and here. So it's not particle-like, where something particle-like would only come through and hit right in the middle, and you wouldn't get any light coming through the next set of slits. Okay, and so the light coming through the next set of slits also has the same wave-like manner where that wave spreads out from its point of origin. And people could see how wavelengths, based on how the wavelengths of the light interact with each other, right? You would get interference if you were, where you would get constructive interference, you get a positive, right, sum of the wavelengths of the light. So you would get interference that was brighter in certain areas, but also you get interference that was destructive, right, that was darker. So that would be destructive, and these would be constructive. And that's something we just kind of need just in a very simple way to understand about light, is that initially, early on, so towards the end of the 19th century even, so, even 125 years ago, this was the understanding of how light was different from matter, right? Matter, particle-like, energy, and light was wave-like, okay? But around that, the end of the 19th century is when we start to see some experiments that go to challenge that current understanding, or the understanding at the time of light and energy versus matter. And so there are a couple experiments that are important that we talk about. Okay. So the first one, and here's sort of a description of this for us, hopefully in a relatively straightforward way. And I write this whole thing out here because these can be some somewhat challenging experiments to understand and conclusions to understand. So the key is sort of understanding what is the experiment and what is the conclusion that comes out of it. And the first experiment that we're going to look at is what's called black body radiation. Really, it's a phenomenon that people observed. Okay, so black body radiation. So first off, what is black body radiation? And so what people knew at the time is if you took something considered to be a black body. So a black body is something that is that perfectly absorbs light. So it doesn't emit any light, it doesn't reflect any light. It's just a piece of matter, something that you would see as black because it's absorbing all of the wavelengths of light. And if you took that and you heated it up, you can think about sort of a piece of charcoal or a piece of iron, and you heated it up, you heated it very, very, very hot, it would start to give off light. Okay, so as you get it hot, it gives off light, and classical physics predicted at the time, so classical physics is really the physics of particles. And so classical physics predicted that those hot objects, when you heated them up so hot that they would glow, that they would give off not only visible light, right, but also significant quantities of ultraviolet light, X-rays, etc. Okay, turns out that's not what's observed. If you heat up a piece of a black body, a piece of metal, say a piece of iron, you can think of to help you visualize that. You could think of a piece of iron that you stick into coals and you heat it up until it glows, like a blacksmith might do before the blacksmith hammers on it because it's nice and malleable when it is that hot. Well, so it's glowing metal, right? So classical physics says, yeah, it's giving off this light that we can see, but it has to be giving off all kinds of energy that we don't see with our own eyes. And so what happens is it would give off tons of energy very, very quickly, and that isn't what actually happens. So Max Planck is the person who comes up with an explanation for why all of the energy of that black body isn't just given off very, very quickly, but really says that it's only emitted in certain ways. And so his explanation, we're not going to get into all of the underlying math of it and whatnot, but he comes up with an explanation where he proposes that, well, the radiation that's emitted from a black body comes in these discrete packets. Okay, so it's not actually a continuum of energy that's given off like you would get if based on classical physics. What it is you get packets of energy that are given off, and those packets he calls quanta, right? Or a quantum is the singular version of that. And really what these discrete packets are is the smallest these quanta are the smallest little packet of energy that can be given off by a certain substance. Okay, and so based on his explanation, he says that, well, okay, if you have the energy given off by a black body is given off at different wavelengths, the energy of a given wavelength of light is the energy of one quantum, and that is going to have energy that's equal to h nu, where h is a constant. Okay, and so he came up with this constant. Nu is the frequency, right? And so if you just look at one packet of energy, that one packet has the energy h nu. If you look at the total amount of energy that an object gives off when you heat it up, the amount of energy that it gives off as light is going to equal n h nu, where n is just the number of quanta. Okay, and so the constant that he proposes for this eventually becomes known as Planck's constant and has a value of 6.626 times 10 to the minus 34 joule seconds. Okay, and so a little bit we can go to a simulation again, one of these PhET simulations, and start to think about sort of what was really observed with this black body radiation. And so we'll share that. There we go. Okay, so here's the black body radiation PhET simulation. And so here, what you would expect based on classical physics is essentially that at any temperature, the amounts of light are essentially, or the relative amounts of light are going to be essentially the same. Now, what really happens is as the temperature of an object is increased or decreased, right, you'll notice that it's not just that the amount or the height, so you have the spectral power, how much light is being given off as compared to, so we have the temperature here, right? So the temperature you can adjust up and down. As you do that, at higher temperatures, more light is being given off, so we can zoom out. At higher temperatures, more light is being given off, but it's not just more light is being given off. You can see this peak of light is shifting at higher temperatures farther out, farther to the left, farther to a smaller wavelength or a higher frequency. And so one of the big things that Planck concludes is that the energy of the light is related to that frequency, right? So at lower temperatures, we zoom in, right? At lower temperatures, you'll see the peak, right, starts to shift to the right towards longer wavelengths or lower frequencies, okay? And so it's based on this type of observation and a whole lot of things that are sort of beyond my pay grade and in terms of the physics of it that Max Planck comes up with his explanation for black body radiation. Okay, back to here. Yeah, and so this is one of the key equations for understanding the energy of either one packet of light, one quantum of light, or many packets of light. For example, if you think about n, this is just the number of packets, right? So if I have 2 packets of energy, it's twice as much energy. Okay, so how does that? Why is that important? Well, you can start to just think about energy from the standpoint of, well, what if we have just a color of light, right? What is the energy of one quantum of light of that color? And so for that, we can really just do a simple calculation where we can say, well, the energy is equal to h nu. And so h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Okay. Times, so we're going to take that same color of light, the green light that we just looked at before, and we're going to find out how much energy that light has. Well, this is given to us in wavelength, right? Now we can go and say, well, what's the frequency of it, like we did in the calculation before, or we can just plug in, since we know that nu is equal to c over lambda, we can just plug that whole thing in there. So you can say 2.9979 times 10 to the 8th meters per second divided by 513 times 10 to the minus 9 meters, right? Or in our case, I'll do this down here. We've already calculated the frequency. So if you've already calculated the frequency, you can just plug that in. So 6.626 times 10 to the minus 34 joules times seconds times, and we can just go back up to our, there we go. Where do we go? Right in here, the 5.84 times 10 to the 14th hertz. Okay. And a which is 1/2. So you can see the seconds are going to cancel out. Okay, and so you wind up with, I'll put the value down here, it's really simple, 3.869 times 10 to the minus 19 joules for that one quantum, right, of green light. Okay, but that's just one packet of light. And so you can think about a packet of light is being given off by an atom, okay? Well, if you have a mole of atoms, let's say you have a sample that has 1 mole in that sample, and each of those atoms in that sample give off 1 quantum. Now, that's a high efficiency, but it gives us an idea of how to understand the total amount of energy given off by a sample, as opposed to the amount of energy in one packet of that same green colored light. So in this case, you can say, okay, well, if each atom in a 1 mole sample emits 1 quantum of light with that same wavelength, what's the total amount of energy, right? And so for that, you just say, well, E is equal to N H nu. So that would be E is equal to N times H times C over lambda, right? And so you could plug all of these things in the same way, depending upon what you're given. And in the case of N, well, 1 mole, okay, is 6.02 times 10 to the 23rd atoms, right? So N would be 6.02 times 10 to the 23rd. So here you could say E, and remember, mind you, this is E total, right? That's the total amount of energy given off by a sample, as opposed to the amount of energy of the wavelength of light. And so here you could say, well, the energy here, E total, is going to equal 6.02 times 10 to the 23rd times 6.626 times 10 to the minus 34 joule seconds times, and I'm just going to put in H nu, 5.84 times 10 to the minus 19 joules. Hold on, that's not right. Times 10 to the minus 19, 1/2. There we go. Okay. Excuse me, that should be times 10 to the 14th, but I'm getting my numbers mixed up in here. That should be times 10 to the positive 14 hertz. There we go. Okay, and so if you just do that quick calculation, you could see that 1 mole of that green light would have 2.26 times 10 to the minus 4 joules of energy to it, right? And so again, relatively simple calculations. You're using a couple of simple equations. And so sort of to summarize the equations that we're looking at here, right, we've got 3 key ones that we've really looked at. C is equal to lambda times nu. We've got E of a quantum is equal to H nu, and E of sample, or E total, will equal N H nu, where N is the number of quantum. Okay. And so those are some of the calculations that you'll see in some of this really basic beginnings of understanding how these packets of energy, how much energy these little packets have, really. Okay.
Professor, I just have a question about the calculation. I just want to make sure I did it right. How is it that it's -4? I'm getting a really large number.
Maybe I did.
Did we convert? Do we have to convert it or
Oh,
something?
you know what? I think I know what I did wrong. Hold on.
Okay, so it's okay.
Yeah, I forgot to multiply it by a mole. Is that? Check this out again.
I just got 10 to the 4th, not 10 to the -4.
Yeah.
Okay, cool.
Actually, we got 10 to the 5th. So, yeah, that was my mistake here. So let me fix that on here. I forgot to multiply by a mole. Good job, me. Okay, so this one, come on, should be 2.33 times 10 to the 5th. Is that better?
Yes, thank you.
There we go. Yeah. Okay, so that's sort of the relationship between these little packets of energy and light and how many you might have. And that's sort of one of the first experiments to really start to challenge light as a wave, right? Because if light is coming in packets, well, we don't think of waves as being packet-like, right? A wave is that, if you think back to that puddle, right? The wave propagates out from where the rock hits it. It's the energy that's dispersing, that's moving out away from where that pebble hits the pond. But it's not like I have a lot of little packets of energy, little chunks of energy that are coming out at us. And that's one of the things that's sort of profound about Planck, is he starts to describe the light energy as coming in these little packets. And there's another experiment that starts to challenge the understanding of matter and energy as being very different, right? In particular, of light being only wave-like. And that's the photoelectric effect. Okay. So the photoelectric effect is another really big and important experiment for us to understand, and that's we'll talk about what the effect is, and the person who really gives a nice solid explanation for it is Albert Einstein, and he's the one so he actually comes up and wins a Nobel Prize for this later. But what I want to do for this is, I think, a very, very hard concept if it's not explained quite right. So first and foremost, we're going to go over an explanation, and we're going to look at a PhET simulation that I think does a great job of illustrating what the photoelectric effect is. Okay, so what the photoelectric effect is basically, like in the 1880s, people don't know the scientist who discovered this, but the discovery was made that electrons can get ejected from a metal surface. What do we mean by that? Like literally, the surface can give off the electrons when you shine light at it. Okay, so you shine light at the surface, so the light hits the surface, hits this metal with enough energy that it imparts that energy to the electrons in the metal, and some of the electrons have enough energy to eject, to go away, to completely leave the metal surface. And so an observation, right? And that's one of the things about this, is these observations are leading to people studying them and finding that a lot of the classical mechanics, the classical doesn't describe it well. And so here, what they find is electrons get ejected from the surface when they are hit with ultraviolet radiation. However, the frequency matters. The frequency matters a lot, because low frequency, remember ultraviolet, if you think about where violet is on that spectrum, right? Violet is at the shortest wavelength on the visible spectrum. which is the highest frequency. And as we know, as frequency goes higher, the energy goes higher. And so if you hit it with ultraviolet light, a very high frequency light, right, it ejects electrons, but light of low frequencies doesn't. Okay, no matter how high the intensity, no electrons get ejected. When we say intensity, intensity of light, how bright it is, okay? How bright is that light, right? Turns out that intensity is related to how many of these quanta are shining at the surface, as opposed to how much energy. And that wasn't understood well at the time. And so as the frequency of the light is increased from low frequency to a high frequency, there's this point at which electrons begin to be ejected, okay? And so at that frequency, okay, beyond that frequency, electrons get ejected. And so this gets a new name, and the name of that frequency is called the threshold frequency. And we're going to see that illustrated in this PhET simulation here in a second, and classical physics just can't explain it. So we're going to go to PhET simulation. Oh, this is photoelectric effect, which actually, give me a second, I can open up. So we're going to go to this page. Okay. So this is the page for the photoelectric effect. You'll notice that this is a JavaScript. And so on this one, it's important to understand that if you want to run it, you need to make sure you have Java uploaded on your computer if you want to play around with this particular one. But this is actually one of my favorites that the PhET program has put together. And so let me share what the photoelectric effect simulation is. Okay, so hopefully you guys can see this on your screen. So the photoelectric effect. Basically, here's the sample or the experimental setup of this photoelectric effect, okay? What you have is a glass container in this particular case. And this container is in vacuum, right? So, or under vacuum. So all of the gases have been ejected and pulled out of this container. And we're going to look at certain parts of this particular simulation. We're not going to look at all of them. What we need to know is that, so you have this vacuum chamber in here because you don't want the gases to interfere with the experiment that's going on. And so there's our chamber. Inside the chamber, we have a couple of electrodes. So there's one electrode, here's the other electrode. A surface or attached to one of the electrodes, plated out on the electrode is a metal. In this case, we have sodium as our metal. We could adjust that as needed. These electrodes are connected by a wire. And we're not going to deal with the battery now. We're just going to understand that the connection between those electrodes is just through a wire, and we can monitor the current through those. Now, in the current setup, we have no current running through the wire, right? So there's a current of 0. We don't have the light on though. And so here's our light source. Our light source, we can adjust the color of the light or the frequency of the light, right? Higher frequencies in the UV, lower wavelengths. You'll see the wavelength changes, right? The wavelength as I go from left to right increases as we go out to the IR. And then we have intensity. So intensity and brightness. So I'm just going to put this at like a yellow light, and you can sort of see what happens to the brightness of the light. So if I turn it on, I have a little bit of intensity. If I turn it on to a higher intensity, it gets brighter. Okay, so we can adjust those things, the intensity of the light and the wavelength of the light, which we know is inversely related to the frequency. Okay, and as you can see there, these little things that are moving across, those are going to be the electrons that we're going to think about. Okay, so what I'm going to do initially, I'm going to set the intensity at 25%. And what you'll notice is down in the IR, if we have the frequency of the light is in the IR region, or the wavelength of light is in the IR region, no electrons are being ejected from that surface. Now, it doesn't matter if I turn the intensity all the way up, right, still no electrons are ejected. Get the intensity back down to 25%. Okay, and I can start increasing the frequency, right, decreasing the wavelength of the light. And as I do that, there will come a point where we will start to see electrons ejected. Okay, and so the point, the frequency at which the electrons start to be ejected is called the threshold frequency. Okay, now the threshold frequency, right, for a given metal is different, right? So for sodium, we have a threshold frequency right around 540 nanometers. And you can play with this. It's not a particularly exact measurement of the wavelength of the light. But if we change to, say, something like zinc, right, you might find a different threshold frequency. Okay, and so you can see as you turn it up, right, zinc have to go out a little farther, a little farther, a little farther, right, way out into the UV region, somewhere back here. Right, so way out in the UV region is where there's the threshold frequency for zinc is. Right, so different metals have different threshold frequencies. So we're going to take this back down around that 540 nanometers, a little bit more than that. So there's sodium again. Okay, so we've got this green light shining on sodium, and we're starting to eject these electrons. You can see these electrons can be moving at different speeds. Before we talk about the speed specifically, let's talk about more of the number of particles that are being ejected. So I'm going to move this back down to about 532. So we've got some particles that are being ejected right now. If we increase the intensity, you'll notice we get more particles being ejected. Okay, so and these, remember, these are electrons. More electrons are ejected when we have a higher intensity. Essentially, we're hitting the surface of that metal with more packets of light energy, right, which cause more electrons to eject. If you have fewer packets of light energy, right, fewer electrons will be ejected. They're still going to be ejected, but you're just not going to get as many of them. But you'll also notice something about the speed of the particle. So I'm going to set our intensity about 50% now. And I just want us to think about the speed of these particles and how it relates. Remember, these electrons are being ejected because light hits the surface, gives those electrons energy, and some of those electrons will have enough energy to escape. Now, why is that important? Well, if you have a metal surface like sodium, when an electron escapes, you have a negatively charged electron and now a positively charged surface. And that electron is moving away from the surface because it had enough energy to get pulled away or to leave that surface, despite the fact that the positive and negative charges want to be attracted to each other. So you hit it with enough energy and boom, it goes away. It's no longer held into the surface. Now, you'll notice that all of these, these electrons tend to be moving at a very slow speed. No matter if I have an intensity at 100%, right, or an intensity that's very low, the particles that are ejected near that threshold frequency will be moving very, very slowly. Okay, back to 50% intensity. So now, if we increase the frequency, right, make it a shorter wavelength, you'll notice that those particles are moving faster. Right? You hit it with a higher frequency or higher energy light. Now those electrons have more kinetic energy, right? They're moving faster. And we know kinetic energy is related to the mass times the velocity squared. And so if you hit the surface with a higher energy light, those particles move faster when they are ejected, okay? Now, again, below that threshold frequency, no particles are ejected. They don't have enough energy to overcome the attraction between what would be a positively charged surface if that negatively charged electron was ejected, right? So once you get to that threshold frequency, they have enough energy to be ejected, but only that much. And so they're going to move very slowly. The excess energy beyond that's necessary to eject it, right? That excess energy is very small. But as you give it more and more energy, those particles can move much faster. Okay? That's what we're really looking at in this particular experiment. And the whole photoelectric effect aspect of it is something that Albert Einstein explains. Okay? And so what Albert Einstein does, he explains it in the following way. Albert Einstein says, okay, this effect, this photoelectric effect, is due to the energy of the light that hits the surface. Right? It's based on the energy of the light. If the light that hits this surface doesn't have enough energy to cause the electron to be ejected, then that light energy is just going to hit the surface and cause those electrons to move faster, cause vibrations between the atoms, and it'll end up as heat. But if it has enough energy, those electrons can be ejected as electrical energy. Basically, that light energy hits the surface and does work on those electrons, causing those electrons to move away from that metal and start a current. Okay? So what he basically says to this is, well, if it takes a certain amount of energy for the light, where the light hits that surface, and that energy isn't dependent upon the total energy, right? Remember, if we go back to this, the total energy that is hitting this surface, right? The total energy is based on how many quanta there are, right? So if the intensity of the light is higher, you're hitting the surface with more quanta of energy, so more total energy. What's happening though, and Einstein explains, is it's not the total amount of energy, it's the energy per packet that governs whether those electrons are going to be ejected at all. And so you can kind of think about it from the standpoint of, well, how does, at least in a way to sort of visualize this, how might what might this mean about the light? And so Einstein says, well, okay, so the light is actually acting in this particular example like a beam of particles, right? And why a beam of particles? Well, if I think about, let's say, the piece of metal that has the electrons in it as that surface that we're sort of chipping away at, if you will, right? That surface, you want to hit it so hard as to eject an electron. Well, that's kind of like if you're hitting a surface of, let's say, a rock with a tiny, tiny pebble, right? That tiny pebble is just going to bounce off that rock. There's not a whole lot of energy in that pebble. But if you hit that piece, that rock, with a bigger stone that has that's moving faster, that stone that hits the rock will chip off a piece of the rock, and in a sort of analogous way to the electron being ejected from the surface, right? It causes the particle to break off, to be ejected. So you can think about the light as acting more like a beam of particles in this particular experiment, and he calls those particles of light, if you will, photons, right? And the photon is, again, a little packet of energy, sort of analogous to Planck's quanta. And he says the energy of that particle of light, that photon of light, is the same as Planck's h nu, right? So now he's sort of equating, Max Planck's understanding of the energy of a quantum of light to now, oh, well, that quantum of light is just the light acting as a particle also, which is pretty crazy, at least at the time, because this means that what people thought about light and energy is not necessarily the case, right? It's not only wave-like. Light is also particle-like, or at least has particle-like properties. Einstein is really the first to propose this in a really meaningful way. And he does this in a way that allows him to say, well, okay, in order for you to eject an electron, right, the light, those packets of light energy, these photons, have to have enough energy to cause that electron to be ejected. And what this is called, it's the work function okay, of the metal. Okay, and the work function, you can think about it as, well, you're doing work on the electron. You're trying to move an electron with a certain amount of force, a certain distance, basically far enough away that it's no longer held to that surface. So that's called the work function of the metal. And the work function of the metal has a value of h nu 0. And this nu 0, right, that is the threshold frequency of the metal, okay? So nu 0 is the threshold frequency. Right, so that's the minimum frequency of light that will eject an electron. And sometimes, by the way, you'll see the work function. Okay, so this work function is abbreviated. Is actually abbreviated by the Greek symbol phi, right? The circle with the line through it, right? And that's going to be h nu 0. And so what his equation says is kinetic energy of the electron that's ejected, okay? So this is, that energy there, right, is 1/2 the mass of the electron times the velocity of the electron squared, right? And so that kinetic energy is going to be dependent upon the light that's shining on it, on the metal, okay? So that's the light shining on the metal. Okay, that's that part, minus this work function. And that work function is the energy that it takes to remove that one electron, right? And so the excess energy, right? The excess energy that the electron has, right? That's the kinetic energy. That's sort of the excess energy beyond the necessary energy. And the electron is going to have an amount of that that's basically the difference between the light that shines on it and the amount of energy it takes to eject the electron. Okay. And so this leads to his explanation of the photoelectric effect. And ultimately, since in this explanation, light is acting as a particle, it leads Einstein to the conclusion that light has wave and energy, for that matter has wave particle duality. Okay, and that's a really, really big thing. It's saying that light and energy acts as both a particle and as a wave, right? Okay. And so what we're going to do now, just in the interest of time, we're going to actually do an example problem next time around. I don't think 10 minutes is long enough to really go through all of the explanation for our next example. And so what I'll do now is I'm going to end it here. And I know there's some questions as far as some of the material that'll be on the exam, but this is just our just jump in to light and energy, which is again going to be necessary as we start to understand a little bit more about the structure of the atom and how atoms interact with each other, as well as how atoms interact with light. Okay, so I'm going to stop our recording here.